Okay, today's lesson we're going to look at section 27.1, C.1. We'll follow it up with C.2. We're looking at stellar magnitudes, that's the C.1. And then star classifications, C.2. On the magnitudes on this first part, I'm breaking it into two parts. We're going to be looking at star magnitudes on what we call apparent magnitudes. And that is abbreviated by little m that you see there in the title slide. Stars between 6,000 and 7,000 individual stars are usually visible to the unaided eye on a clear night away from the city. So if you go way out there, you lay on the grass on a moonless night, deep in the country, you can see between 6,000 and 7,000, depending on how good your eyes are in your field of view. Ground-based telescopes, however, as you see in the picture down below, they can allow you to observe a little bit more than 3 billion stars that are individual. And as we saw from Zoom to Polaris, what we thought was the North Star or Polaris being an individual star, as the technology improved, we found out that one star we're looking at was actually 3. So the numbers will go up. In fact, on the other video with Isaac Arthur on colonizing Proxima b, you found out on that one that the 3 stars there as well. Part of what he's talking about on the way there, that a lot of the stars are not binary. So you're going to see in this slide, we're talking about the percentage that are binary stars. But he's saying it's not as much because now we're actually able to see the red dwarfs we talked about before, the real small ones that if you lay them on the Earth, they would cover between Alton and St. Louis. So some of the stuff we talked about before is coming back again, and technology is able to see these. So we're finding out there's actually a lot of single stars. But that's going to be a while before that actually works its way through the system and into the books. We had the Hubble telescope. That was the first space-based telescope where we actually got above the atmosphere and the city lights and where it's really dark in space. And that could see about 1 trillion or 1,000 billion. So the ground base is 3 billion. We're seeing 1,000 billion individual stars with the telescope. And it's well on into its life, but everywhere they point at a dark spot long enough, like a time exposure, we find out there's many, many more stars. So they're looking at about 1 trillion. And so we also see some of the more recent generation, the Herschel telescope, the Kepler telescope, the Fermi, and Hubble. So these are all named after famous astronomers or scientists. This visibility, quote unquote, of an individual star depends on how bright it is and how far it is. And so we're looking at star brightness versus star closeness. And so those combination factors are the ones that we're able to pick up even with our technology. And because of this, we use 2 scales to describe the brightness of the star. One scale is based upon how bright the star appears from Earth, and the other scale is based on how all the bright stars would be if you line them all up the same distance. And we're going to talk about that where those little graphics show them all lining up. So how would they appeared versus if I could line them all up, if we can get them all the same distance, so it's not a distance thing, how bright would they actually be? That'll be the second type of brightness. So right now we're not talking about that, we're talking just about apparent brightness. So by definition, how it appears from Earth is how it appears, or its apparent magnitude. We use special instruments that are attached to telescopes, and they can measure the light from the star and how it appears from Earth. And there's always dust in space, a lot of it, which tends to filter it. So with special filters, we can see through that dust. We're saying, well, it appears to look this color or this brightness. And so they actually will do work where they look at magnitudes and they start measuring that. And we can actually measure distance in astronomy by comparing the brightness of objects to known reference points. And we'll talk about that in a minute. The scale's kind of backwards, what you would expect, almost like a golf score. So the measurement of a star's brightness is then assigned on a scale. The brightest stars have the lowest value or most negative, either the lowest positive or the biggest negative. So it's kind of going backwards on the scale, like a golf score. The lower the score, the better. The dimmest stars have the highest values, highest positive values. And we're talking about the apparent magnitude numbers. We'll talk about that in a second. And what they do is a little brief one. We're talking about some of the ones they could see. Magnitudes of -1, that's very, very bright. You might see one star that's over that. That's our sun. Magnitude stars of 0, you might catch 3. This is out of 100 star, 5,100 stars they did, I'm sorry. Magnitude of +1, so I'm getting dimmer. So I become more positive, the more dimmer it is. About 8 stars I would see. 2 is about 35, on down to magnitude 7. We're getting past the part where you can't see it with your eyes. You're going to need like binoculars. So we're getting at 6, about 3,500 stars you can see. When you hit 7, you just can't see it. It's not visible to the unaided eye. So this is the apparent magnitude scale. It goes in opposite. The brighter, the more negative. Our sun actually has an apparent magnitude of -26.8. So it's obviously the brightest thing in our sky. The moon, on a full moon, when it's reflected, would be a -12.5. So it gives you an idea how the scale works. Venus, which you tend to see in the morning or in the evenings, depending on what time of the year it is, a -4.6. One star, Sirius, or the dog star, is a -1.46. So it's bright. Once you get to +7, you're going to need help, even with really, really good eyes. +6 is about the limit. The most powerful telescopes can detect stars with apparent magnitudes of about +29. So when we're about +6 for our vision, these guys can go out to +29s. And this is not, it's more of a logarithmic. There are stars that are about 1.5 times billion fainter than the faintest star we can see without a telescope. So if you have one, you dimmed it 1.5 billion times, now you're talking about something on a magnitude of +29. Very, very dim. And here's a chart where they've actually mapped some of these out for a reference scale for beginning astronomers. So you're looking at, in this little circle, it looks like a dark spot, but if you train this on here, you find out that even that dark spot has, those galaxies are in there. Very faint. Those are galaxies. Those are not individual stars. There might be some in the front part of that field that are individuals, but for the most part, those are galaxies. So they each having 100 billion or more stars in them just to get that light. The unaided eye can see stars with apparent magnitudes, again, it's about +6 or a 6th magnitude star. Very, very bright stars would be on the 1st magnitude for the most part, except for Sirius, which is a minus. Most of them are around +1. They're what we say, that's a bright star. Some of the planets, the moon and the sun, have negative magnitude objects like Venus, sometimes Jupiter. And that's because the objects in the sky, they're brighter than 1st magnitude stars, so they're negative. So as you see on the scale here, once you get plus, these are bright, dim. These are really bright. Now you're talking about Venus, Sirius, the moon, the sun. They start going high in the negative part. And we said also Sirius is the brightest magnitude star for us at apparent magnitude of -1.4. As I said before, the sun is at -26.8. Well, Polaris, the one you zoom to, which is actually 3 stars, it's a +2.5, so it's even on the dimmer side. So there's little Polaris, the North Star. You can see it. It's well within our limit of +6. But right about here, where you can't see anymore with the eye. And the Hubble Space Telescope is one of the first, is about like a +29. Not quite. And some of the new ones we have are getting up in the +50s. So it's moving as technology and techniques improve. We can see better as well. And so the next part we're going to talk about is absolute magnitudes as compared to apparent. So that'll be for part 2. So I'm going to stop here now.